Hi, and welcome back to my C# OpenTK 2D game engine/framework series. This is part 3, where we're going to be focusing on shaders. If you recall from the last video, we got a triangle to render on the screen, but it was just a black triangle, there's no color, and this is because my graphics card is supplying a default shader for debugging purposes. For you, it could be black, it could be white, or it may not be showing anything at all. Because, if your graphics card does not supply this default shader, then it simply you won't see anything. If that's the case, by the end of this video, you will see a triangle rendering, and I'm going to show you how to change the color of the triangle using a shader. So I think it's best for us to start off by answering the question, what is a shader? A shader is a program you write in a C-like language called GLSL. We can write these programs and upload them to the graphics card, compile, link, and use. Shaders specialize in vector and matrix manipulation. They do this fast, and they do it well. There are several types of shaders, such as fragementShader, vertexShader, geometryShader, and several others. I don't believe all of them are programmable, but the only two that we're going to focus on for this course is the vertex and fragment shader. These shaders run at specific sections of the graphics pipeline. For example, the vertex shader is called for every vertex, and the fragment shader is called for each pixel as it fills it in. So as you can imagine, to give our triangle some color, we're going to need to program this in the fragment shader. So let's get started. We need to create an integer to keep track of this program, because, for instance, when you generate a buffer that returns an integer or an unsigned int, and the gen vertex array returns an unsigned int, well, it's the same thing for the shader. So let's call it private int shader handle, and then I'm going to go down to the description after this and just copy paste it in. I don't want to type it out by hand because it can be kind of painful. It is this section here, and I'll walk you through what it is. Manually typing this out in C# is just inside a string format is just kind of annoying, and we'll eventually be switching this to load from a file. So you have to state the version, which we are in core 3.3.3.0, and this layout, location equals 0. Remember in the previous video I had said I was just going to give you the code for something, and you have to trust that it will just work. That's this part here. This vertex attrib pointer 0, we're specifying its location is equal to 0, and I don't think we need to specify it for the fragment shader. When you copy paste this in, it'll be what I've just put on here. I don't want to re-record that. So that's how you're enabling this pointer here. You're specifying the layout. You don't have to use a layout. You can remove the layout portion, and then you can write a call that will look for any attributes that are in your shader, and it'll return the position for you so you can enable it and work with it. But you might as well just lay it all out, and then it saves you and OpenGL some time. So what we'll need to do is generate an ID for the vertex shader. So do int vertex shader ID equals gl.create shader, and then we have to provide it a enum for the shader type. So it's shader type dot vertex shader. And here's a list of some of the other shaders that I was talking about. Again, we're only going to focus on the fragment and vertex shader. So we'll do vertex shader, and then we'll call, we have to give it the source, so we'll do gl.shader source. That will be equal, that's not equals, it's a state machine. So vertex shader ID, because we're specifying which one we're supplying the source for, and then the code. So that would be vertex shader, and that's this up here. And then now, all we have to do is just compile this shader by doing gl.compileShader and then the vertex shader ID. Okay, so now that we have that, we probably want to check to make sure there were no errors, because we can pull that out of OpenGL. And once we compile this, there is an enum that comes with the OpenGL 4 namespace that we can use. So we'll call this method here gl.getShader, the vertex shader ID, and the parameter we want is compile status. And then we have an out var for this, so out var vertex shader compilation code. And then what we can do is we can check if the vertex shader compilation code isn't equal to, and this is an integer, but we can just cast it, so int, and then all.true. And if it does have an error in the code, we'll go ahead and write that out to the console. Right. And we can call gl.getShader info log for that vertex shader. I think for OpenGL it's getShader IV or something along those lines. Vertex shader ID. And then that's all we need to do for the vertex shader. Eventually we have to link these, but now we can move on to the fragment shader. So we need an integer to keep track of its ID. So int fragementShader ID equals gl.createShader and shader type dot fragmentShader. Then we have specified source, shader source for the fragment shader and the fragment shader code up here. And then the same thing, gl compile shader, fragment shader ID, and then we'll also get the compilation status code, gl.getShader, fragment shader ID, shader parameter dot compile status, out var fragment shader compilation code. And then we'll check if the fragment shader compilation code isn't equal to int all.true. We'll write it out to the console. And we'll just go ahead and let the execution run. This is just a debug build, but once we finally go through and abstract all this out, we'll kind of determine if we want the application to terminate in this scenario. But for now, we'll just let it run and we'll just keep an eye on the console if we think anything is wrong. So now we actually have to create the shader program, because this was just the shader source for vertex and fragment. Now we have to create the actual shader. So we're going to say our shader handle, which was what we declared up here, is equal to gl.createProgram. The gl.attach shader handle, and then we need to attach the vertex shader. So we'll do vertex shader ID. And then we need to do the same thing for our fragment shader. And then now that we've attached them, we just need to link them. So the reason we need to link them is because in order to render anything, we need to have a vertex and fragment shader. And there might be a situation where we want to pass some data from the vertex shader into the fragment shader, so we need to link them together. And we will cover that here in this episode too, about how we will pass information through them. So what we'll do is go ahead and link it. So we'll do gl.link program shader handle, and then we need to do some cleanup. So once we've done this, the shader is now on the graphics card, and it's now an application that we can use. We don't need a reference to the fragment or vertex shader ID anymore, because now it's just part of this program. So we're going to go ahead and just detach the shader from this shader handle by doing gl.detach shader handle, vertex shader ID. I'm just going to copy this down and replace this with fragementShader ID. And then we can delete both of those shaders because they're already compiled and they're linked into the program. We don't need them sitting on the graphics card memory anymore. So we'll just do some cleanup here and do gl.delete shader and vertex shader ID, delete shader, fragment shader ID. Okay, so that looks good for getting our shader going, but let's go ahead and take a look at what we have so far, and then we're going to make some changes to our vertices and then how we pass that information in. But for now, we'll just stick with just getting a color to display. So we don't need to change anything up here. Yep, so it's a vec3, so we have 0. And then this final one, I believe, is alpha. I will look that up and make sure I address that in the next video and confirm what this last one is for the vec4. But you can just use apos here, which is the position we're passing in, .x, y, and z. You can type it out, but each one at a time if you really wanted to. So you could do aPosition.y, aPosition.z, but OpenGL has a way to just specify them in the order that they're in just to kind of shorthand it and save some time. Okay. Yep, and then our out color, this is just going to be a red. So this would be our red, green, blue, and then this is the alpha. So 1, this should be a red triangle. And then now all we have to do is tell it to use the program before we call bind and draw arrays. So we will do gl.use program shader handle. And if we did everything correctly, there should now be a red triangle. Let's give it a shot. And there we go. It is red. Okay, so that's cool and all, but I think we want to do something cooler. What if we want to linear interpolate this? So we want to have the bottom left be red and the bottom right be green, and then the top to be blue. How would we do that? Well, it's actually quite simple now that we have a shader. We need to update our vertices to have these colors. So let's change up the comments on here a little bit. So this is our positions, X, Y, Z. And then what we'll want is colors. And we said we want this one to be red, we wanted this one to be green, and we wanted this one to be blue. So let's go ahead and type those out. So red would just be 1.0f, and then zeros for the rest, 0.0f. And then for green, the second one would be a 1, so we'll do 0.0f, 1.0f, 0.0f. And then we want the final third one to be 1. So 0.0f, 0.0f, and 1.0f. Get our comma in there. And that should be good. So now we need to tell the shader that these are the values that we want to pass into it. So what we can do is we'll make another attribute here. We'll call it layout, and we'll set the location equal to 1, and it'll be an in vector 3 because we have 1, 2, 3, and we'll call it a color. I'm using a because it's an attribute. Once we get into uniforms, I will be prefixing those with a u, but just want to call out why I'm using a in here. There's no what do you call it, key word that you can't use in a language like position or color. It's just the naming convention that I use. And then we need to, in the main method, determine what that color should be that we're linear interpolating to. So we need to pass this into the fragment shader. And the way that we do that is we give our vertex shader an out vec4 called vertex color. since this is an out variable, I'm not applying an A or a U. And then in our main method, we want a set the vertex color equal to vec4, and we'll use the color we passed in, so a color dot RGB, and then 1 for the alpha. And then we need to update our fragment shader to accept this vertex color, because the vertex shader is running first, and then the fragment shader runs after it. So the way that we pass it in is we just make an invec here. So invec4 vertex color. The names have to match here. And then in the color, we're just, instead of setting it to red, we will just set it to the value that we determined in the vertex shader. So this should be all we need to do for the shader, but as you can see, this changes the structure a little bit. Because originally we just had 3 floats that represented it. Well, now we have 6. So it makes sense that we would need to update the attribute pointer to reflect that. Because right now if we just did 3, it's expecting 3 to read these in bytes of 3, and then that doesn't really make any sense, and it's not the right amount that's being allocated. So we just simply update that to a 6, because there's going to be 6 of these. 1, 2, 3, 4, 5, 6. That's the stride of this, and it's starting at position 0, which is here. And then now we're able to pass this in, but the challenge we have here is oops, I made a typo here. The challenge is we need to be able to also pass in the A color from this. And the way that we do that is we have to call GL dot vertex attrib pointer. Just like up here, remember how we specified the location equals 0, or layout equals 0, layout equals 0? Well, now we want location of 1. So now we need to get the vertex attrib point, set the vertex attribute pointer of 1. Its size is 3. It's still 3. We're still doing 3 here for the color for red, green, and blue. And then we need to tell it its type, which is a float. Our values do not need to be normalized. They are already normalized. The stride is still 6 times the size of float. That doesn't change because that's how many bytes it needs to allocate. But this is where we need to set the offset. So our offset will then be 3 times the size of float. So that, let's go over this one more time up to the top here. There's 6, so 6 times the size of float. That's what we're passing in. Our first attrib pointer 0 consists of 3 vectors, and it starts at position 0, and it moves 3, and it's there. And then we have to enable it, which we'll also need to do for this one as well. And we'll call this 1, or not call it, that's the one that we have to enable. And then we're saying in here, this 3 there's the size of 3, so it's 3 floats, don't need to normalize it. It's still in the stride of 6 because there's still made up of 6 of them here, but instead read 3 and start at the offset of 3 where the size of 3 floats. So 0, 1, 2, 3. So it starts here for it. And if we did everything right, this should now linear interpolate to it. Fingers crossed. And there we go. That is set up exactly how we expected. So, oh, that's interesting. Yes, after this, we're going to fix this. This is not how we want it to work. Okay, so our bottom left is red. Our bottom right is green. And our top vertex is blue. So what we want, notice how when I stretch this out and I change the size of it, it's not really what you would expect. That's because we're not properly handling the resize event. So let's go back into our GameEngineTK.core, and we need to hook onto this method. And this is actually pretty simple to do. we will call the game window dot resize, and we'll subscribe to it with the resize event args. And this is all the information we need. And we'll call GL. We will need to import this. Remember to use OpenGL 4. Dot viewport. We're at 0, 0, but then the width and the height is what matters. So we can just reference the game size, game window dot size dot x, and game window size dot y. And that should be all we need to do. And let's confirm. Okay, so if I change the size, yep, it's fitting. So I can make this tiny, it'll still make it. I can expand it out and it'll use up the full screen. And I think that's where we'll wrap this episode up. In the next episode, we need to address the elephant in the room. This is obviously disgusting to have all of this logic inside of your game classed here. You know, these should typically be pretty thin, and you hand that off to classes. So what we'll do is we'll break the shader logic out into a class. This is something that we'll be able to reuse. We're going to update this so we can pull it from a file, and because this is just not maintainable to just keep shaders in like this. It might be okay if you had something for just, you know, debugging purposes and you just wanted to hard code it. I guess I could see that, but not for your production build. So we'll update it so it loads it from a file. I will show a technique that I've been using. It is borrowing a concept by a YouTuber called Cherno, and he has an OpenGL series that he does in C++. I highly recommend you check it out, even if you're not interested in doing C++, because he can explain this stuff a lot better than I can. The guy, he knows his stuff. All right, so like and subscribe if you like what you see, and I'll catch you in the next video.